All right, so the topic for today's presentation is I'm going to be introducing CXL 3.0. And we're going to be talking about the expanded capabilities for increased scale and optimized resource utilization that CXL 3.0 brings. My name is Ishwar Agarwal. I am right now working at Intel Corporation in their data center architecture team working on Xeon. And a few weeks ago, till about a few weeks ago, I used to be working at Microsoft Azure data center architecture. And I recently served as the co-chair of the CXL Consortium Technical Task Force. Right? That's a little bit about me. But we are here to learn a little bit more about CXL, so let's get started. So for people who are not aware, CXL is a consortium which is formed for an open standards for high-speed communication. It is comprised of hyperscaler companies such as Google, Microsoft, Meta. It's comprised of silicon vendors such as CPU vendors such as Intel, AMD, ARM, and of course IP vendors, Synopsys, Cadence, as well as memory vendors, Micron, Hynix, Samsung, etc. So that's just some of the names that I've read out, but of course there are a lot more companies. So at this point, we have more than 200 plus member companies. This is an incredibly strong consortium on the lines of PCIe. And we are actually very proud of our board of directors that have actually formed part of this consortium. So the consortium has gone from strength to strength. It was originally conceived in 2019, March 2019. But the actual consortium kicked off when the first spec was released back in September of 2019. So as you can see, in the last 3 years, this consortium, which was formed with 10 companies to start with, has gone to over 200 companies and has released 3 generations of specifications, starting with 1.1, 2.0, and 3.0. And this has been a very torrid pace of spec release, much more than what you normally see in our industry, right? PCIe, for example, has a much slower cadence than this. And CXL's cadence has been very, very fast to start with, because there has been so much of evolution of the specification since the time it has been released. It's a pretty brand new concept. It enables a whole new set of usages and capabilities. And that takes a lot of iteration, and there has been a lot of member feedback and a lot of innovations that have come into CXL, and that has been responsible for these quick generational releases. We do expect this cadence to slow down over time, right? And it's going to be more on the lines of what the PCIe spec cadence is going to be going forward. By the way, if you guys want to ask questions or just pause me at any time, and we can make it more organic and more of a discussion than just me talking. That's totally fine. Or we can do it at the end. That's fine too. Cool. So we're going to talk a little bit about CXL 3.0 specification and what are the new things it has introduced. And to start off, what was the big motivator for 3.0, right? So as a whole, the big motivation for some of these specifications comes from usage models, right? That's really what we're trying to serve. We're trying to serve our customers at the end of the day. And the use cases that were driving some of these 3.0 specification features, the industry trends, were need for higher bandwidth, high performance accelerators, and system memory. Those are the 2 things. I mean, there's a whole bunch of words in the slides, but really at a high level, it is memory that is driving the need for greater bandwidth and high-performance accelerators, right? And the high-performance accelerators is a bit of an umbrella term. It actually talks. It actually has subcomponents to it, such as smart NICs, your GPU type engines, etc. And memory, as we know, is one of the leading causes of pain. It's a bottleneck for almost all kinds of CPU efficiency and core performance. Our cores are getting stronger. The number of cores is getting more and more as we go up in CPU generation. And compute performance is extremely limited by memory. And CXL is yet another way to alleviate that particular bottleneck. So CXL 3.0, for the very first time, introduces a brand new concept called fabrics. And we'll get into some details, some pictures about what fabrics really means. It's pretty interesting. It's really, it actually is very thought-provoking. And so I'll get into a little bit of what fabric capabilities are. And we'll talk a little bit about multi-headed and fabric-attached devices, including fabric-attached memory. So we'll talk about that. And along with that comes improved capability and scalability that comes with fabrics. We have also gone over and beyond what previous generations have done in terms of memory pooling, in terms of support for switching, bringing it on par with PCIe. We have introduced new coherency capabilities that were not there in CXL in 1.0 and 2.0. And we have formalized our software ecosystem as well as standardization of our interfaces to better enhance software's capability to develop standard drivers. Question?
Yeah, is there any hardware at all in any of these generations that's actually available? If you can say it's backward compatibility, with what? Is there anything that actually exists that is backward compatible? I'm not saying there isn't, I'm just saying I don't know.
No, that's a very good question. So actually, I'm just going to talk about backward compatibility. Okay, yeah, absolutely, yeah. So the question really is about the last bullet on the slide, which is fully backward compatible with previous generations of CXL. What does that really mean when we don't have CXL devices in the wild today is really, I think, how I interpret your question. Right, and a very good question, and I'm going to talk about it as well. But before we get there, I want to emphasize two other things about CXL 3.0, which is with CXL 3.0 we doubled the bandwidth over previous generations. It's now running at 64 gigatransfers per second, whereas previous generations were running at 32 gigatransfers per second. And one of the big USP for CXL is latency. So we have doubled the bandwidth without introducing any latency over previous generations. Let me address the previous question, and then I'll take your question. Is that okay? Okay, so the last bullet, which is fully backward compatible. The backward compatibility story is super duper important for any standards to actually have meaningful legs going forward. So what I mean by that is this. When CXL 1.1 was first introduced, the specifications always precede actual products by some amount of time, right? Depending upon the industry, depending upon the product segment, it precedes. CXL is something that gets implemented in CPUs as well as in devices and switches. The lag time for such things to go from specification, and especially with CPU development timelines and switch and device development timeline is pretty long. That's like one of the longest in our industry. And so 1.1, CXL 1.1 implemented CPUs are, I would say, imminent. 2.0 is going to be in the next year or two. And then comes along 3.0. So why does backward compatibility matter if 1.1 is not even released? It matters because the backward compatibility offers the same guarantees that we have with PCIe today. With PCIe today, you can take a PCIe Gen 3 card and plug it into a PCIe Gen 5 system, and it works. Right? And the other way around. And yes, yeah, and the other way around. You can take a PCIe Gen 3 capable system and put in a PCIe Gen 5 card, and the link degrades, or the link trains up to only 8 gigatransfers per second, and it just works. And that just works is the ROI that developers need, because they're investing a ton of money into developing systems and cards, and they want to make sure it has legs. I will take this gentleman's question because I saw this hand first, and then I will come back to you, sir. Is that okay?
When you say that you doubled the bandwidth versus CXL 3.0,
Yeah.
The bandwidth is really riding on PCIe.
That's right.
So what I understand is you're inheriting the bandwidth.
That's right. That's correct.
So does that mean that CXL requires PCIe 6?
I will answer that in the next slide. Is that okay? I'll take your question.
I know. Along with this question.
Mm-hmm.
I'm sorry. Along with this question.
Yeah.
Have you guys got an emulator or something to work with?
What?
Some sort of emulation or something?
For what? Sorry.
For CXL.
So that would be, yeah. The question was, do you have an emulator to work with? An emulator or a BFM or some of these collaterals are implementations of the specifications. I believe there are companies out there that are developing BFMs as well as IPs to conform to these standards. But the standards are independent of these emulators or BFMs or bus functional models or other validation collaterals that are needed. Was there anybody else? Sorry, I missed. Yes, sir.
Yeah, so I think what the question is, you talked about how you can plug something from a different generation in, so it's really both directions.
That's right.
It's not just backward compatibility. So if you do have one you can buy now, you can plug into a later one, you can plug a later one to the earlier one. You won't obviously get the intersection of what
that's right.
the capabilities are, but at least it'll work.
And we call that backward compatibility because you degenerate to the least common denominator. Oh, the question.
We can try to let you get through your slides because you're going to answer a bunch of this stuff.
That's right. That's right. maybe that's right. Maybe that's right. But this is more fun, you know. I like it this way. It's more of a conversation.
Okay. Just if you're going to do it that way, then just leave.
Yeah, I will try to do that. All right. So to summarize some of the feature enhancements of CXL over generations, right? So let me see if the mouse pointer, yeah. So with 1.0, which was released back in 2019, this was at a max link rate of 32 gigatransfers per second. And I don't get into a lot of the technical details of 1.0 and 2.0 in this presentation, but the observation by the gentleman was absolutely right, which is CXL uses PCIe electrical and physical layers. And so in that sense, CXL 1.1 and CXL 2.0 was riding on PCIe Gen 5 electrical and physical layers, and CXL 3.0 is riding on PCIe Gen 6 electrical and physical layers. And as PCIe Gen 6 is at 64 gigatransfers per second, PAM4, so is CXL 3.0. And what I want to make a small but important clarification over here, which is you can get some of the CXL 3.0 features even if you run it, even if you run your PHY at 32 gigatransfers per second. You don't have to run your PHY at 64 gigatransfers per second, right? And that is essentially the features of CXL 3.0 are tied to the flit size of 256 byte flits. 256 byte flit can be carried over 32 gigatransfers per second. It does not have to run at 64 gigatransfers per second. All right. So CXL 1.0 defined the concepts of type 1, type 2, type 3 devices, which are accelerators and memory buffers. All that has been carried forward. With 2.0, there were a bunch of new capabilities that were introduced, and I'll recap some of these capabilities in some pictures in the next few slides. But the quick summary is that essentially CXL 2.0 formalized a bunch of memory usage models with pooling, switching, global persistent flush for persistent memory, as well as link encryption and integrity. So bunch of formalization of CXL memory usage models with 2.0. And I'll recap some of that in the pictures that will follow. With 3.0, all of that is there, but we have enhanced it with multi-level switching, bringing it on par with PCIe. We have optimized a lot of the data flows so that a lot of the data flows that used to rely on data having to bounce to the host first before going to a peer device can now go peer-to-peer, more optimized data flows. We have enhanced the coherency semantics within CXL to be even more friendly to implement. We have introduced a brand new concept of memory sharing, and I'll talk a little bit about this in some pictures. And some of the limitations of CXL 1.0 and 2.0, these are some limitations that we fixed. And the fabric capabilities is something I'll show in some pictures in the next few slides. Yes, sir.
Is it really 68 bytes?
The question is this really 68 bytes? Yes, this was indeed, this was actually 68 bytes. And the extra 4 bytes came from 2 bytes of CRC and another 2 bytes of physical layer header information that was being sent. So 64 bytes was matching the cache line size, and then the extra 4 bytes were the CRC and other overhead, physical layer overhead. Okay. All right, so quick recap for people who are not familiar with 2.0. So one of the most exciting features of 2.0, one of the most useful features and most talked about features of CXL 2.0 was the concept of memory pooling. For people who are not familiar with memory pooling is a way of making your memory more fungible across multiple hosts. So in the cloud, in the data center, one of the biggest problems is this concept of resource stranding. And essentially today, the way we provision memory on a given blade is that we physically provision and fix allocate a given amount of memory to a blade. If that blade is not using its memory, that memory is essentially wasted. Memory represents the most expensive component on your server. It far outstrips everything else. And so this memory being wasted is a massive, massive problem. It's the biggest thing that one can do to reduce TCO today in the data center in terms of CapEx. Nothing else comes close. Maybe power. But anyway, memory pooling is a way to alleviate that by essentially using memory as a fungible resource. So what you have over here is multiple devices, D1 through DN. And these devices are CXL devices that have some memory. And this memory is connected to a CXL switch. The hosts are connected to the same switch. And now what you can do is at runtime, right, dynamically slice the amount of memory that is attached to each device and be able to allocate that to different hosts. So two things that are important. One is you can slice that at fine granularities. That means these granularities can be as low as hundreds of megabytes. It doesn't have to be the entire device or not. It can be, let's say you have a 4 gig memory attached to it, you can slice it n ways. And then you can dynamically allocate each slice to a given host. Right? So that's the concept of memory pooling. In this picture, it's color-coded. So for example, D2 has some amount of memory allocated to H1 and some amount of memory allocated to H3. Okay. All right, and the second big concept in CXL 2.0, just to recap, was the concept of a switch. Switch is just like a PCIe switch. Essentially, it was meant for fan-out purposes. And it helped with expanding the amount of system memory on a platform. This was to overcome the limitations of the number of DDR channels that we can physically provision on CPUs today. If you wanted to get more capacity with cost-effective DIMMs, there's no good way of doing that, so you had to find new ways to attach more system memory to the platform, and the switch was allowing us to do that. Okay? Questions?
What makes a CXL switch different from a PCI Express switch?
What makes a CXL switch different from a PCIe switch? It carries CXL semantics. It carries the CXL protocols. It has a different set of routing rules, different set of decoding rules based upon what the CXL specification defines. All right. Now we come to CXL 3.0. So with CXL 2.0, the switch was limited to a single level switch as we saw in the previous picture. With CXL 3.0, our switch is now more capable. It's just like PCIe switches. You can cascade the switches. You can use the switches as fan-out switches. You can have multi-level switches. You can have devices attached to different hierarchies in the switches. It becomes more, I would say, more fungible. I don't know what's the word I'm looking for, but essentially more malleable. Right? That's the word I was looking for. So you can now have switches arranged in different topologies, just like PCIe. That's the first one. The next one, this one is pretty interesting. This is the device-to-device communication. Right? So we talked about the fact that CXL allows for more efficient data movement between devices without having to bounce them to host first. So that's called device-to-device communication or peer-to-peer access. So in this picture, what's happening is you have a CXL switch to which a number of hosts are connected. You also have a number of devices connected to this switch. So one of the concepts in CXL is that you can do a logical device assignment, right? So in this picture, all the blue devices are assigned to host H2. So they're part of what's called a virtual hierarchy in CXL. And now the host H2 along with D1, D2, D5, and D6 is one independent system. Now when D1 wants to talk to D6, let's say D1 is a NIC, D6 is a memory buffer, the NIC wants to DMA some traffic into a memory buffer. If D1 wants to talk to a NIC, the NIC wants to talk to a memory buffer, D1 wants to talk to D6, Today, the way the flows work, the NIC first has to DMA that data into host-attached memory, and only then can a consuming device actually retrieve it out of host-attached memory. You first have to go use DDR, and then you have to read it out of DDR. That's pretty suboptimal because you're using the host. You have two problems there. One is the host becomes a bottleneck, right? If you have multiple peer-to-peer accesses, you just can't keep up because the host's root port is going to become your bandwidth bottleneck at the PCIe port or the CXL port. The second problem is you're using the bandwidth of host-attached memory for essentially facilitating I/O to I/O flows, which means that host memory bandwidth is not being utilized by cores doing other things, right? So essentially, you have two problems there. And this flow essentially alleviates both those pressure points by allowing that bandwidth to remain outside the host's domain and allowing this to be more efficient. Question.
You're also transferring it twice. So you're
That's
using
right.
twice the bandwidth as well as that.
That's right. The comment was you're also transferring that data twice, absolutely. So you're using twice the amount of power, twice the amount of latency, twice the amount of everything in the system. Yes. I'll sorry this hand first.
On a previous slide, you had mixed host allocations of memory.
That's right. That's right.
In this one, it's implied that you can't do that. Is that no longer correct?
The question is, in the previous slide, I was showing a picture of memory pooling with sub-device granular memory assignment. In this picture, I'm showing multiple devices attached to the host. These two pictures are representing two layers of abstraction. They're not trying to imply that in this picture I cannot do memory pooling along with this. The CXL switch is actually defined as a pretty capable entity that allows for devices of different kinds, accelerators, including PCIe devices, as well as CXL memory buffers, to be one of these D1 through Dn. So you can actually have all of these different combinations at the same time below a CXL switch. Is it a follow-up or okay?
So yeah, I asked that question so I can answer.
Yeah.
So once you do that, you start entering into routing issues, oversubscription issues.
Yeah.
Topology issues.
That's right.
Later on in your presentation, will you be talking about those implications, or is that for another time?
The question is, when you define something as powerful as that, you're essentially giving yourself a rope to hang yourself with. And the answer is yes, and that's true in a number of different scenarios, right? If a system designer, under provisions or oversubscribe a given port, you can have multiple devices talking to one destination, and you can run into bandwidth latency, queuing effects, all kinds of negative things. But that's a system design issue. That's not a specification issue. That's a bad system architecture from a design and flow perspective. And so I will not be getting into that. That's a different implementation problem. Question?
Same question he had about
Okay.
multiple
Yeah.
clients.
Okay.
Get out of my head.
The comment was, get out of my head. All right. Want to make sure everything gets captured here. Okay, what's memory sharing? Memory sharing is really, really cool, I think, but really interesting too at the same time. Okay, so we talked about the concept of memory pooling, right? Memory pooling was a way to make memory more fungible. We talked about all the cost associated with the data center and all that stuff. But the most important thing, one of the most important thing about memory pooling was that a given slice of memory within a given device could only be assigned to one and only one host at any given point in time, right? If there is a physical range of DRAM, let's say a 1 terabyte range of DRAM, that 1 terabyte of range is, let's say that's my chosen granularity of assignment. That 1 terabyte can only be assigned to one host and one host only. That means that nobody else is touching it. And CXL actually specifies that nobody else should touch it, and the device should actually make sure and all security is guaranteed. That's what memory pooling was. However, there are scenarios where it makes sense for memory to be shared across different hosts. We did not have that with CXL 1.0. We did not have that with 2.0. With 3.0, now we have the concept of memory sharing. In memory sharing, now the same exact region of memory can be shared among multiple hosts. And the CXL device is the one that is going to maintain hardware-based coherency across these different hosts at a cache line granularity. And the CXL specification provides the semantics for how to do so. Okay, so that's the difference between pooling and sharing. And now you can.
One question about the memory sharing.
Uh-huh.
So basically, one physical CXL memory can be shared by multiple hosts, right? And multiple hosts can assign a different virtual address for the same physical CXL memory. So how cache coherency will work?
Okay. The question is, if you have if you have multiple hosts that are sharing a physical range of memory, and they're using different addresses to get to that same physical memory, how is cache coherency maintained across these different hosts? The answer is cache coherency is always maintained at a physical address, on a physical address basis. It does not relate to virtual addressing or linear addressing that is being used by different hosts. Okay? So that's true even for multi-core systems in today's system, in today's servers, right? Each core could be running a different process, and in case of shared mem, they could be using different, virtual addresses to get to that same physical memory. The host snoop filters, etc., are all running on physical addresses to maintain coherency. Okay. So you can take coherence, you can take memory sharing and memory pooling and club them together. So like I was saying, the CXL switch is a pretty powerful entity. And this entity can now support devices that are capable of pooling and sharing at the same time. So I'll come back to you. So in this picture, right, let's see if I can find a good one. Okay, yeah, D4. So this device D4 has a range of its memory. It's called S1 over here. That is a shared range. And this shared range, because it's a shared range, host 1 has a copy of that shared range, host 3 has a copy of that shared range, host hash has a copy of that shared range. It also has some ranges that are not shared, that are simply pooled. And those are hard allocated to only one host at any given time. There could be other devices that are not doing sharing, they're just doing pooling. So essentially the CXL switch allows for both of these things. CXL defines the concept of an entity called a CXL Fabric Manager. This is a formally defined entity in terms of its APIs. And these APIs are what allows for system management to control which slices are pooled, which slices are shared, and who they're getting pooled to and who they're getting shared with. So all of this is through this standard API called the CXL Fabric Manager. Some people ask, where does the CXL Fabric Manager live? The CXL Fabric Manager can be implemented as a piece of firmware that's running inside the CXL switch. It can be a piece of firmware that is running on a microcontroller that sits on a PCB. For example, it could be running on your BMC. It could also be a piece of firmware that runs as an agent inside a host that is a controlling agent, as a control agent. Okay, I'll take your question.
So you solved the most difficult problem of cache coherency, but you could solve the quotas or some kind of bandwidth quotas so that there is oversubscription, or you have a simplistic model?
The question is, how did you solve the problem of cache coherency, but you did not solve the problem of quotas? I'm not fully sure I understand the question, because the question of bandwidth oversubscription is a system design issue. It's not a specification issue. It's if you have in any system today, whether it's PCIe, NVMe, CXL, DDR, what have you, right? You could always end up with oversubscription of a given resource if you allocate the resource to too many sources, and if you have too many sources trying to get to the same resource at any given time. CXL does define a policy of QoS control that allows for resources to be able to indicate back to multiple sources. I have reached a level of usage where I might start underperforming, and you need to back off. The concept of quality of service is definitely there in the specification. Okay. All right. Just want to make sure I keep an eye on the time. All right. This slide is about fixing one of the limitations that some people were pretty upset with in terms of 1.0 and 2.0. CXL 1.0 and 2.0 did not allow for multiple devices of all types below a root port. It's an esoteric limitation, but Be that as it may, it got fixed in CXL 3.0. I don't know if anybody in this audience cares, so if not, I'll just move on. All right. I'll get to CXL fabrics now, which is one of my most favorite topics. So with PCIe and CXL thus far, we followed a tree topology. And a tree topology, as people may be familiar with, allows for one root of the tree, which is the host, right? And then the tree fans out from that host, and the tree can be comprised of switches, bridges, and endpoint devices, right? But they all lead to one root, right? And that's how PCIe is structured, and that's how most of CXL is structured. CXL fabric, on the other hand, is a different concept altogether, which allows for a non-tree architecture, right? This non-tree architecture. What this basically means is, in this architecture, and this is an optional part of CXL, it doesn't have to be this way, you can create a fabric comprised of CXL switches. So the CXL switches act as the glue of the fabric. And to each switch, you could have some nodes, and the nodes act as the leaves of the fabric. And what this allows for is that it allows for every node in this fabric to have a peer relationship with every other node in that fabric, right? You can have any node talk to any other node. The most common fabric is, of course, Ethernet, but CXL is not trying to get to Ethernet levels of scale. It is much smaller in its scope and ambition. We recognize that we are based on PCIe physical layers, and there are limitations, inherent advantages and limitations that come with that. So to that extent, CXL is trying to limit its fabric capabilities to within a rack, or at max couple of racks. I can't imagine it being more than that. The specification defines for up to 4,096 endpoints on this fabric, but in real systems, I'm not sure I will get anywhere close to that. So as I was saying, the nodes could be anything. In this particular example, the nodes are combination of hosts. It can be CXL type 1 or type 2 devices, which are accelerators. It could be devices with memory expanders. One thing this slide didn't call out was the nodes could even be PCIe endpoints, right? So the nodes could be one of many things as far as the standards definition is concerned. So how do you use this construct? How do you use CXL fabrics? One of the things that the CXL specification, the 3.0 thing defines is the concept of fabric attached memory, right? And then we stuck a global in front of it. So it became global fabric attached memory. So what's a GFAM or a fabric attached memory? The fabric attached memory, think of this as very similar to what the type 3 device was, which is the standard CXL memory device. Except now it also understands fabric semantics, right? And the reason I call out fabric semantics is because fabric has a few more pieces of information that is sent to the receiving node in order to be able to decode which node is talking to it and how to be able to route responses back to it. So this GFAM device is nothing but your type 3 device being used in a CXL fabric. And now we're going to see why this and I'm introducing this as a construct first, and in the next couple of slides, we're going to see how useful this construct is. The construct of a GFAM device is also independent of media types. It could be DRAM-based media, it could be persistent media, it could be flash, it could be whatever, right? It does not care. All right, so here's an example of how fabric and a GFAM or a global fabric attached memory device could be used. And this example is, in this example, you have, let's say, a host, right, which has a bunch of machine learning accelerators. And one of the limitations with ML accelerators, especially in the case of training, is that your model size may or may not fit within the amount of memory that you have on the device. And if you have such a cluster of such ML accelerators connected to multiple hosts, you could essentially put a bunch of GFAM devices to be used fungibly with multiple accelerators, right? And these accelerators are essentially going to be able to use this GFAM memory as additional memory as either scratchpad or to store a training set model which doesn't fit in local memory. So that's what this particular picture is essentially showing. Another use case, HPC analytics. So in this use case, it's turned a bit upside down. So in this case, it's actually the host that is connected to the CXL switch. In the previous case, it was the accelerator that was connected to the CXL switch, right? So in this model, what's happening is you have a bunch of NICs that are using, and this is the HPC analytics use case. So in this case, what's happening is you have a bunch of RDMA traffic happening. You have some MPIs being sent from one host to the other host for coordination. And these NICs are going to be able to talk to multiple hosts, and these hosts are going to be able to talk to a bank of NICs for essentially sharing of resources. And one of the things that I described earlier was how CXL switches allow for one device to be able to talk to another device directly. So these NICs are going to be able to talk to the GFAM devices directly. Yes.
How does this relate to DPU? I don't know what a DPU was until yesterday, and then I went to the version of it. So basically, it looks like a NVMe drive semantics, but it actually could be anything practically. And you just talk. Are any of these related to that? There's so many different ways of doing it.
Okay, so I'll try to paraphrase the question. How does this relate to a DPU, right? Or how does a DPU fit into this model? To me, DPU examples that I've seen are usually used for offloading specific types of functionality onto a piece of silicon. So essentially, there's nothing but an accelerator with enhanced capabilities. For example, you could offload your software-defined networking stack onto a DPU, right? That's an example of a DPU. So in this picture, a DPU could simply be an accelerator. And you can have a CXL-based DPU. If the accelerator wants to talk to memory, you could have a DPU that is talking to memory. So that's how DPUs relate to CXL. Oh, this is a nice animation. I love this one. So this is, I think, my second last slide. So oops, my bad. So this is showing how the CXL fabric could be used to create a spine leaf rack architecture. So the lighting is bad, but I hope you guys can see this. Essentially, what we have over here is a rack with multiple blades, right? And what is happening over here is that you can have a blade that is a NIC blade, an accelerator blade, and accelerators could be DPUs. You could have memory blade, and these are essentially your leaves. My voice is getting hoarse. Sorry. And these leaves are connected by essentially CXL spine switches. So that's what's happening in this particular picture. This is essentially a way of creating rack scale architecture using CXL fabrics. So this is a quick summary for CXL 3.0. So we have fabric capabilities. We talked about switching. We talked about enhanced memory coherencies that allow us to do peer-to-peer. We double the bandwidth without adding any latency. And we maintain full backward compatibility. All this is to target some brand new usage models, such as memory sharing, support for multi-headed devices. Multi-headed means devices that are being used at the same time by multiple hosts. Expanded support for type 1, type 2 devices, as well as global fabric attached memory. And finally, our call to action is to download the CXL specification, check us out on social media, and consider joining us to make the specification even stronger. I think that's all I have. All right. Sorry about my voice getting hoarse, but questions, other questions? Yes?
We assume that the other functionality from Express 5.0, 6.0 is in the CXL switch, like downstream port containment, authentication, all made it into the CXL switch.
The question is, can we assume that all of PCIe Gen 6 features have made it into the CXL specification? The answer is everything that is in PCIe specification is part of CXL.io. So everything gets carried into CXL.io. Now, there are parts of the CXL Gen 6 specification that are also useful for CXL.cache and CXL.mem. Downstream port containment is an example of that. And on a case-by-case basis, yes, they are also getting incorporated.
Is there a boundary on the number of CXL switches you can have in a system?
I don't believe so. I think it's the same as PCI at this point. Oh, yeah. Is there a boundary or is there a constraint on the number of CXL switches you can have? And I think I don't believe so.
So then the follow-up question to that is, with you start getting into some pretty well understood networking problems at that point, right? And different topologies to alleviate some of those problems. So, realistically, how many switches can you put together into a link in a CXL environment? Again, assuming infinite amount of PCI bandwidth.
The question, oh, I didn't see the sign, but I think the sign, I don't know.
You're not saved by the sun.
No, don't worry. So, okay, I'll repeat the question. The question was, so once you get to a certain number of switches, especially with the CXL fabric, you get into some pretty well understood fabric or network issues, things like congestion management, dynamic routing, all of those kinds of issues. And then how does CXL propose to manage that beyond a certain number of switches? So initially, when you asked me the question about switches, I was thinking about fan-out switches when I was saying no constraint. In CXL fabrics, I think realistically, the answer is it's TBD. There is some basic minimal congestion detection and routing that is being defined, but it is nowhere close to the level of Ethernet or InfiniBand or anything else that is meant for scale out, large scale, thousands of nodes. It's nowhere close to that. The max number of ID space that we have constrains us to 12 bits, right? So 4096 is the total number of endpoints you could have. Realistically, I don't anticipate the number of switches that you see in that fabric to exceed more than 8 or 12. That's what I think, but we'll see.
I can put 8 to a nice little torus. So.
That's just my opinion on that one, but yeah. Go ahead.
Can you expound on how it's working with peer-to-peer and how that works with CPUs that are really designed that way?
The question, if I heard it right, was can you explain how peer-to-peer works? Is that right? Okay.
And also how you're able to make that, how you can extend out the capabilities of the CPU that's not really designed that way. They're using like QPI buses and things like that.
Okay. So how does that work for CPUs that are designed for QPI buses and for things like that? Okay. So first thing to note is that the peer-to-peer net traffic that we were talking about is between devices, right? So it's not it's not peer-to-peer between CPUs. Right? CPUs, when they communicate with the peer CPU, if they are part of the same coherent system, they're using CPU proprietary protocols such as QPI, UPI, hypertransport, whatnot, right? CHI, what have you. That's not using CXL. CXL is not meant for SMP, symmetric multiprocessing. It's not meant as an inter-CPU interconnect. It's not meant to replace UPI, QPI, hypertransport, whatever. It's only meant to optimize device-to-device peer-to-peer. Device-to-device peer-to-peer is supported even in PCIe today. It's called peer-to-peer. And the mechanism is very similar to what the CXL mechanism is very similar to what PCIe's mechanism is. CXL is in fact leveraging one of the new concepts in PCIe, unordered I/O, UIO. And essentially it's leveraging that mechanism to be able to do UIO to something called HDM. HDM stands for Host Managed Device Memory. It's essentially a CXL construct that allows for CXL devices to advertise memory as system addressable memory. Right? And the same constructs of how UIO is used to send traffic to host attached memory is the same construct that is being applied over here for CXL devices using UIO to send traffic to another CXL device that has system addressable memory. Okay. Yes.
Yes, maybe to elaborate on this one. There's an initiative within PCIe to standardize what we call inter-systems bridge, which would allow to have CPU to CPU communication, and it's supposed to become an addendum to PCI Spec 6.0, which eventually would got to mix and match things. Compute units, storage unit, memory units, accelerators, because CPUs are running out of steam. So that's the function we're driving.
Thank you. I can't repeat all of that though.
See Hendrik for details.
There you go. Go ahead, and then I'll come back to you, sir.
The mapping table that maps a logical device or memory sharing between various CPUs and memory, you said it can be changed at runtime.
That's right.
So how do you take care of things that are in flight while this is changing?
Okay. The question is the mapping table of memory that is being either pooled or shared can be changed at runtime. 5 minutes, okay. That can be changed at runtime. So how do you take care of in-flight transactions that are being used by a given CPU? So the theory of operations on that one essentially centers on a flow that has been defined in the CXL specification. It centers around dynamic capacity devices. And what that allows, the dynamic capacity device is actually defined in the CXL spec, but at the OS level, what's happening is memory is being brought online when memory is allocated to a given host, right? So there is a CXL memory driver that communicates with the OS memory manager and uses a memory onlining flow to bring a certain address range online in this OS's address map. Once memory is online, the OS is free to allocate address ranges from that newly brought slice to applications and be able to use page tables to be able to allocate virtual memory to that particular address range. Similarly, when pages are taken away, when memory has to be deallocated, the CXL device communicates with the CXL memory driver to say, hey, I want this memory back. Can you please ask the OS to give it back? So the memory driver communicates with the OS memory manager, says, hey, I want this back. OS memory manager says, fine. Let me see who else is using this in the page table. So essentially, it goes through an offline flow. The offline flow may or may not be successful depending on whether pages are pinned, but that gets into a whole different level of complexity that we should probably not get into right now. But that's essentially the flow. Another question? Okay, sorry. Yes.
So today I learned from the fiber channel community that they have an F pin for awareness, debugging, telemetry. Is there something like this planned for CXL?
The question was, there is something called an F pin in the fiber something? Oh, I'm sorry, I'm not aware of that. I don't know what that is, and
It's an event notification if you have a bad link or if you have coordination of services.
Okay. So the question is there a way for CXL devices to communicate either device-specific errors or link marginality errors up to some standard software? The answer is yes. Actually, that's pretty well defined for multiple different reasons. So there is a DRAM subwork group within the CXL consortium, and that has defined a pretty standard mailbox communication mechanism with the device driver to notify drivers of all kinds of media-specific and media interface-specific errors to a driver. So this is very similar to what the CPU does. So in the CPU today, when you have DDR, DRAM errors, they get correctable errors, uncorrectable errors, poison, etc. There's thresholding built into that. All of that gets reported through machine check architecture. That infrastructure has been, I wouldn't say replicated, but leveraged to report the same information to a CXL device driver. Similarly, link marginality issues, etc., can also be up-leveled up to standard software. I didn't know what an F pin was, but that sounds similar. All right, sounds like we're getting wrapped up over here. Thank you.